Hello universe navigators, welcome back to Coded Universe. We've previously journeyed through the fascinating terrains of trees and binary trees, uncovering the secrets that lie within their labyrinthine branches. The thrill of discovery doesn't end there though. Prepare to delve deeper into the world of data structures. Today, we're setting our sights on a new territory: binary search trees and balanced trees. If you enjoyed our adventure through trees and binary trees, you're going to love today's exploration of binary search trees and balanced trees. Think of a library with an ingenious sorting system. The books aren't just tossed anywhere on the shelves. Instead, they're organized in a certain way that makes it easy to find the one you're looking for. This is similar to how data is arranged in a binary search tree, or BST. In a BST, each node has up to 2 children. The child to the left of a parent node holds a value less than that of the parent, while the child to the right holds a value greater. So when you want to insert a new node, you start at the root, and compare the new value with the current node's value. If it's less, you move to the left child. If it's more, you move to the right. You continue this process until you find an empty spot where the new node fits perfectly. Inserting a book in a binary search tree is just like finding the perfect spot on the shelf where the book fits right in order. Now what if a book is outdated? Picture it. In the grand library of our binary search tree, a dusty tome has served its purpose and must now be retired. This is akin to the deletion process in binary search trees. You see, deleting a node from a binary search tree is not as simple as plucking a book from the shelf. The library must maintain its meticulous order. If the book is a standalone volume, represented by a node with no children in our tree, it's an easy task. But what if it's part of a series or a node with 1 child? A suitable replacement must be found, perhaps an updated edition or the next book in the series. The real challenge arises when our book, our node, has 2 children. We must find a successor that maintains the order of our binary search tree. This is achieved by choosing the smallest book in the right subtree or the largest in the left subtree. It's all about keeping the library up to date without disrupting the order. Searching in a BST? Picture yourself playing a game of hot and cold. You're blindfolded, and your objective is to find a hidden treasure in the room. Each step you take, you're told whether you're getting hotter or colder. The same principle applies when searching for a node in a binary search tree. Starting at the root, your search direction is guided by whether the node you're looking for is greater or lesser. If the node is less than the current one, you move to the left child. If it's greater, you proceed to the right child. Just like in the hot and cold game, each step in a BST gets you closer to your target. The path you follow, whether left or right, is determined by comparing the node you're searching for with the current node. Each choice narrows down the search until you find exactly what you're looking for. AVL trees are like a well-balanced seesaw. Ever been to a park and noticed how a seesaw works? When one side is heavier, it goes down, and the lighter side lifts up. But imagine a magical seesaw that always stays perfectly balanced, no matter the weight. That's what an AVL tree does in the world of data structures. Just like the magical seesaw, an AVL tree maintains its balance after insertions and deletions. It does this through a process called rotation. The tree checks its balance after every insert or delete operation. If it finds that one side is heavier, it carries out a rotation to rebalance itself. This balancing act is vital. It ensures that the tree remains efficient for search operations. In this sense, our AVL tree is like the perfect librarian, always keeping its books in order for the quickest possible retrieval. They automatically keep themselves balanced, ensuring no side gets too heavy. Imagine a dance group where every move is precise. Each dancer, just like a node, has a color, red or black. The dance floor, that's our tree. Now the rules of the dance are simple but crucial. Every dancer starts on the same foot. In our case, the root is always black. There's no step or path where you'll have 2 red dancers or nodes in a row. The dance floor, from every dancer to its descendant offstage dancers, has the same number of black dancers. This ensures that no one dancer or path is longer than the others by more than a factor of 2. These rules might seem strict, but they're what keep our dance group or red-black tree in flawless harmony. Each dancer knows their place, their steps, their rhythm. Red-black trees ensure that no dancer, node, overshadows another, maintaining perfect harmony. You've just navigated the structured jungle of binary search trees and balanced trees. It's been quite an adventure, hasn't it? We've explored the intricate workings of binary search trees, compared them to a well-organized library, and discovered the magic of insertion, deletion, and searching. We've then ventured into the realm of balanced trees where we've seen how AVL trees, much like a well-balanced seesaw, maintain equilibrium automatically. And let's not forget the red-black trees, where every node, like a dancer in a troupe, makes precise moves to maintain perfect harmony. This journey has been about understanding the beauty and logic of these data structures, how they make our programs efficient, and how they mirror real-world systems. It's fascinating, isn't it, how the world of programming often mimics our own. If you've enjoyed this expedition and found it enlightening, remember, there's a whole universe of code out there waiting to be explored. And we're here to guide you through it, one video at a time. So, if you haven't already, it's time to join our community of universe navigators. Give us a thumbs up if you've enjoyed this video. We'd love to hear your thoughts, experiences, and questions in the comments section below. And most importantly, don't forget to hit that subscribe button to Coded Universe. There's always more programming adventures waiting for you here. So until next time, keep exploring, keep learning, and keep coding. Hit that like button, share your thoughts, and subscribe to Coded Universe for more programming adventures.